Hello students, in this video lecture I am going to discuss the concept of lower bound, greatest lower bound and meet in a partially ordered set or a PO set. So the first question which arises is, what do we mean by lower bound of a subset of a PO set? So let P less than equal to be a PO set and let S be a subset of P. Then an element X belonging to P is said to be lower bound of the set S if every element of the set S is greater than X. Or in other words, X is less than equal to S for all S belonging to S. So if we try to analyze this mathematical statement diagrammatically, that is, if we see the hash diagram, in the hash diagram, if we would see that if X belonging to P, if this X is a lower bound of the set S, this means that X would be at a level lower than every element of S, which means that X will be here and all the elements of the set S will be at a level above X. So this is what will happen in the hash diagram, just because X is a lower bound and because it is lesser than every element of the set S, so every element will be at a level upper than X and X will be below every element of S. So now coming to a notation that we have for lower bounds. If we are talking of the set of all lower bounds of the set S, then the set of all lower bounds of the set S is denoted by S L, with where L is this superscript. So this is the common notation that we use for the set of all lower bounds for the subset S. Now coming to the next definition, which is the definition of greatest lower bound of a subset of a PO set. What do we mean by greatest lower bound of a subset of a PO set or greatest lower bound of a subset of a partially ordered set? So for this, let us take a partially ordered set P less than equal to, and let S contained in P be a subset of P. Then an element X belonging to P is said to be greatest lower bound of S, or it is called infimum of S, or it is denoted like this, INFS, infimum S. Or in short, we can even write it as greatest lower bound of S if two conditions are satisfied. And what are those two conditions? Now in a layman's language, those two conditions are that if X belonging to P has to be greatest lower bound of the set S, then those two conditions are that X should be a lower bound. Firstly, it should be a lower bound of the set S, and X should be the greatest of all lower bounds. It should be X should be greater than any other lower bound of S. So these are the two conditions that must be satisfied for X to be the greatest lower bound. The first thing, the X should be a lower bound of S, and the second thing, X should be greatest of all lower bounds, which means that if there is any other lower bound of S, then X must be greater than that lower bound. So these are the two conditions that must be satisfied. So mathematically speaking, the first condition, as I was saying, that if X is to be greatest lower bound or infimum of S, or the GLB of S or INFS, whatever, these are different notations. If X is to be infimum of S or greatest lower bound of S, then it should be lower bound of S first, which means that X should be smaller than every element of S, or X should be less than equal to S for all S belonging to S. And the second condition is that X should be greatest of all lower bounds. That is, if there is any other lower bound of S, if Y belonging to SL is any other lower bound of S, then X must be greater than that. Or here, this is the fact that we can write that X is greater than equal to Y, or in other words, because we are in the habit of writing everything in the form of less than equal to, so we can say that the lower bound Y is less than equal to X. So these are the two conditions that must be satisfied for an element X belonging to P to be greatest lower bound of S, where S is a subset of P. So now once we know the definition of greatest lower bound, a few notations in this regard, which are common notations. The first notation is that when you are in a PO set P less than equal to, and when you are talking of infimum of a set of two elements, this means that if you take S to be the set AB, and this S is a subset of P, so A and B are definitely elements of P. So if we are taking S to be a set consisting of two elements A and B of P, then the infimum of this set S we are interested in denoting in a short notation for the infimum of S, or the greatest lower bound of S, or infimum of the set AB, or the greatest lower bound of the set AB. So if the infimum exists, in that case the infimum of this set of two elements A and B is called the meet of A and B, and the notation that we use for the meet is this: A inverted V B, or A meet B. This is the notation for meet of two elements or infimum of two elements A and B belonging to the PO set P. So this is one notation. Now in general, if you have S is any subset of P, not necessarily having just two elements, it can have any number of elements, then the infimum of S, or the greatest lower bound of S, if it exists, then again it is denoted by this inverted Vs, or and this is of course called the meet of S. So these are two general notations that we have whenever we are talking of the infimum of a subset of a PO set. Now with these notations, let us come to a few examples. So the first example in this regard is just similar to my earlier video on the least upper bound. A similar video has been made on least upper bound to explain the concept. So similar examples have been taken so that we can compare both the concepts, the concept of least upper bound and the concept of greatest lower bound. So again, let me take my PO set to be 3, which is a chain of 3 elements. This is the notation that we use for chain. And if we represent diagrammatically the PO set, then the PO set will be something like this. We have given names to the elements A, B and C so that we can refer to them. So this is the chain P is equal to 3, and let us pick up arbitrarily any pair of elements. Let's say I am picking up A and B, and I am taking S to be a set consisting of these two elements A and B, and we want to find out what is the infimum of S, or what is the infimum of these two elements A and B. So infimum of A and B, if we are looking for infimum of A and B, then infimum of A and B would be that element of the PO set P such that that element X belonging to the PO set P, such that X should be less than equal to A and X should be less than equal to B both, and also NX should be the greatest of any such element which is lesser than both A and B. Now we find that if you take a look at A, then A is definitely less than equal to A by reflexivity. Every element is related to itself, so A is less than equal to A. Also A is less than equal to B because A is at a level lower than B. So A is acting like a lower bound, we can see, and A is the only lower bound. This is because this is the only lower bound. There is no other element which is smaller than A and B. From the hash diagram we can see there is no other element which is at a level lower than A and B. So this is the only lower bound, and that way this is the greatest of all lower bounds because there is no other lower bound, and so this A therefore becomes the greatest lower bound of A and B, or it becomes the infimum of A and B, or it becomes in our new notation, it becomes the meet of A and B. So A is actually equal to the meet of A and B. So A meet B is A. Again, if we pick up the elements B and C, let's say I pick up B and C and I try to find out the infimum of B and C. So S is the set of two elements B and C, and infimum of S, which is infimum of B and C, again that is going to be B, because for the same reason, because B is less than equal to B by reflexivity, and B is also less than equal to C from the hash diagram. So B is acting like a lower bound, and so B is a lower bound of these two elements B and C, but B is not the only lower bound. A is also another lower bound that we have for B and C, because A is at a level lower than B. A is also at a level lower than C, so A is also acting as a lower bound. So if we try to find out the lower bounds of the set BC, the set S consisting of B and C, the set of all lower bounds of this, this will be not only A, but not just B, but it's going to be both A and B. Both A and B act as a lower bound, but out of A and B, which are both lower bounds of the set S, which is the set of two elements B and C, the one which is the greatest is B, because B is at a level higher than A. from the hash diagram we can see that. So therefore, and so B is actually the greatest of all lower bounds of B and C, or we can say that B is the infimum of S, or we can say that that B is the meet of B and C, or B meets C is B. So this is one thing that we have. So likewise, if you pick up any pair of elements, this was an example of a chain. If we pick up any two elements, any pair of elements in a chain, we can always try to find out what is the infimum of that pair of elements. Now if you, because here this concept of greatest lower bound has been defined for any subset S of P. In particular, if you take S to be P itself, that is, if you regard P as a subset of itself, because every set is a subset of itself, then we would like to find out what is the infimum of P, or what is the infimum of this whole set A, B and C, and we can find that A is that element which is at a lower level than all the three elements A, B and C, because in the chain 3, A is at the bottom, which means that A is acting like a lower bound. Because A is lesser than or smaller than each of the three elements A, B and C. So A is the bottom element. So this bottom element A is acting like a lower bound, and it is not only a lower bound of the set P, but it is greatest of all lower bounds, because this is the only lower bound of P. So in that sense, this becomes the lower bound and the greatest lower bound, which means that it becomes the infimum, or it becomes A meet B meet C. So this is the bottommost element, which is the meet of B. So the meet of B is A. So this was the first example. Now coming to the second example. Now in the second example, if you take B to be an anti-chain of 4 elements, which means that there are 4 elements in the PO set, which we have named as A, B, C, D, so that we can refer to them. And because it's an anti-chain, none of A, B, C, D are related to each other. And if we try to find out what is A meet B, if A meet B exists, what is it? What is the infimum of A and B? Then we can see that infimum of A and B, or A meet B, doesn't exist, because there does not exist any element X belonging to P which can act as a lower bound for A and B. So because there is no element, if you consider A and B, there is no element which is no element of the partially ordered set P which is at a level lower than A and B. In fact, the elements of the partially ordered set P are not related to each other. So there is no question of an element being at a lower level or an element being at a upper level, or there is no question of an element being greater than the other or smaller than the other, because there is no relation between the elements. So there is no element of the partially ordered set P which can act as a lower bound for these two elements A and B, which means that if you try to write down what is the set of all lower bounds of the set AB, that is ABL, if you try to find out the set, and if there is no lower bound of this set AB, then of course you can't talk of the greatest lower bound, because there is no lower bound, which means that A meet B is is not existing, because there is no lower bound. So greatest lower bound cannot exist. The same argument goes for that B meet C doesn't exist, A meet C doesn't exist. So if you pick up any pair of elements in an anti-chain, not necessarily an anti-chain of 4 elements, but you can have an anti-chain of any number of elements, and if you pick up any pair of elements in an anti-chain, then any pair of elements which you pick up in an anti-chain will never have a meet, just because there is going to be no lower bound of any pair of elements, and if there is no lower bound, then the question of greatest lower bound existing doesn't arise. Again, if you take P to be the whole set, which is A, B, C, D, and if we try to find out what is the infimum or what is the meet of P, if it exists, we then again by the same argument we have that meet of P doesn't exist, because there is no element in the partially ordered set P which can act as a lower bound, or which is such that there is no element X which is such that X is smaller than or X is lower than every element of the partially ordered set P. This cannot happen because there is no such element X. This means that there is no lower bound for the set P, and because there is no lower bound, PL, which is the set of all lower bounds of P, this is an empty set, and if there is no lower bound, then meet of P, this cannot exist because no lower bound is there. So the greatest lower bound definitely cannot exist. So that was the second example. Now coming to the third example, if we take a PO set P whose hash diagram is this, and if we try to find out what is the set of lower bounds for the set S consisting of A and B. These are A and B, and we want to find out what are the lower bounds for A and B. So if you just take a look at the hash diagram, then we can see that F is at a level which is lower than A and B. So F is acting like a lower bound because F is smaller than both A and B. So F is a lower bound. Then for the same reason, E is also a lower bound of A and B because E is at a level lower than A and B. So E is also a lower bound. And this bottommost element, which is inverted T, that also acts as a lower bound because T is at a level lower than A and T is also at a level lower than B. So T is also acting as a lower bound, which means that the set of all lower bounds of the set S is consisting of these three elements, and therefore definitely it's a non-empty set. But despite of the fact that the set of lower bounds of S is non-empty, still infimum of S or the greatest lower bound of S or meet of S or A meet B, this does not exist because if you just take a look at these three lower bounds which are E, F and T, inverted T, the bottom element, then this is how the lower bounds are placed in the hash diagram. Out of these three lower bounds, E and F could have been could have played the role of greatest lower bounds, but if one would have been greater than the other. But if you see E and F, they are non-comparable elements. None of them is greater than the other. So although lower bounds are there, these two could have been possible greatest lower bounds had one been greater than the other, but E is not greater than F and F is not greater than E. In fact, they are non-comparable. There is no relation. So there is no greatest lower bound of the set S, although lower bounds are there, but greatest lower bound doesn't exist. So this was the discussion about the set S is equal to AB. Now if you take S to be CD in the same way, that is these two elements I am taking C and D, then if you try to find out what are the lower bounds of the set S, where S is the set consisting of two elements C and D, then we can see that just below C and D A is there. So A is the lower bound. In the same way, just below C and D, B is there, so B is the lower bound. For the same reason, E is a lower bound, F is a lower bound, and the bottom element is also a lower bound. So the set of lower bounds is non-empty, but again C meet D or the infimum of S or the greatest lower bound of C and D, this doesn't exist because out of all these lower bounds, that is A, E, then you have the bottommost element which is T, inverted T, then F, and then B. Out of all these lower bounds, none of them is the greatest. In fact, these two possible lower bounds could have acted as greatest lower bound, provided one would have been greater than the other. But as far as A and B are concerned, none of them is greater. In fact, they don't bear any relation with each other. They are non-comparable elements. So greatest lower bound of C and D is not existing, which means that the meet of C and D doesn't exist. So even though there are so many lower bounds of C and D, but the greatest lower bound or the infimum of C and D or the infimum of S or the meet of C and D, this doesn't exist. And if we talk of the meet of the whole set P, where P was the PO set whose hash diagram was given over here, then we can just see that the meet of this whole set, the meet of this particular whole set, the meet of this set is given by this particular element, because that is the bottommost element, because this bottommost element is behaving in a way that this bottommost element is less than equal to P for every P belonging to P. So every element of the partially ordered set P, this partially ordered set P, is greater than the bottommost element, which means that the bottommost element is acting like a lower bound. And since this is the only lower bound of the partially ordered set P, because there is no element other than this bottommost element, which is lesser than this T. There is no other lower bound. This is the only lower bound of the partially ordered set P, which means that this is the greatest lower bound, or this is the meat of P. So meat of P is the bottom element. That is what we have. And now so this is what has been written in the last line, that meat of B is the bottommost element, which is inverted T. So this is the last line which has been just exhibits this fact. Now coming to the fourth example, which is the example of the PO set power set, which is one example which we always take. We always discuss this particular PO set because this explains most of the concepts. So if X is any set, then the power set of X, which is the set of all subsets of X with respect to the inclusion relation, that is with respect to the relation is subset of or is contained in, we know that this is a PO set. This has been discussed in many times in my earlier videos. And if you take here X can be, this capital X can be any set. In particular, if you take capital X to be equal to 1, 2, 3, the set consisting of 3 elements, then in that case power set of X, because X has 3 elements, so power set of X has 2 to the power 3, which is 8 elements, and which are listed over here. So these are the 8 elements of power set of X, and they will form a PO set with respect to inclusion relation, and this is the hash diagram. So this we have discussed many times in my earlier videos, and the hash diagram also has been discussed in detail. Now if we try to find out what is the meat of singleton 1 and singleton 2, which are elements of power set of X, then singleton 1 and singleton 2, if we just take a look, then phi, which is at the bottom, which is the bottom element, is acting like a lower bound for singleton 1 and singleton 2, because it is smaller than both singleton 1 and singleton 2. So this is phi is definitely a lower bound, and there is no other lower bound of 1 and 2. From the hash diagram we can see that singleton 1 and singleton 2 don't have any other lower bound. So this is the greatest of all lower bounds for singleton 1 and singleton 2. So this phi is the infimum of singleton 1 and singleton 2, or it is the meat of singleton 1 and singleton 2. So singleton 1 meet singleton 2 is phi. Again, let us try to find out what is the meat of this element 1, 2 and the element 2, 3. So the element that element of the PO set Px or power set of X, which is acting like a lower bound for these two elements, is 2, because we can see that this singleton 2 is just below 1, 2, this particular element, and 2, 3. So singleton 2 is acting like a lower bound. But if we try to find out what are the lower bounds of this set 1, 2 and 2, 3, then we'll see that singleton 2 is not the only lower bound that we have. Phi is also another lower bound that we have for these two elements, because we can reach phi from these two elements, we can reach at the bottom to phi. So phi is also acting like a lower bound. So there are two lower bounds that we have for the element 1, 2 and 2, 3. This set, there are two lower bounds, but out of these two lower bounds, you have this 2 is here and this phi is here. So the one which is greater is singleton 2. So this is the greatest of all the lower bounds that we have, and therefore this 2 is acting like a greatest lower bound, or it is acting like infimum of this set 1, 2 and 2, 3, or it is the meat of 1, 2 and 2, 3. So that was the meat when you pick up two elements. Now if you try to find out the meat of the whole set, if I try to find out what is the meat of P, then meat of P should be that element X belonging to P such that X is less than every element of the PO set P, or X is less than equal to P for all P belonging to P. And we can see that that particular element which is lower or which is smaller than every element of this PO set is phi. Phi is at a level which is lower than all the elements of this PO set. So phi is smaller than all the elements, which means that phi is acting like meat of P. So definitely meat of P is existing, and it is equal to phi in this case. So that was the fourth example. And now coming to the chain of real numbers, because it's a chain, the set of real numbers is a chain, it's more than a PO set. With respect to the usual less than equal to relation, the usual sense in which we understand less than equal to in the set of real numbers. So this PO set is a chain, and also we can see that if we pick up any two real numbers x and y, they will always have a meet, because x meet y is infimum of x and y. And if we compare x and y, then either x will be less than equal to y or y will be less than equal to x. One of this has to happen. So if x is less than equal to y, then this means x is, this particular x is smaller than both x and y, which means that x is acting like a lower bound, because x is less than equal to itself and x is less than equal to y. So x is acting like a lower bound, and this is the only lower bound of x and y that we have. So this is the greatest of all lower bounds of x and y, which means that x meet y is the greatest lower bound of x and y, or infimum of x and y, or this is this x meet y is x. And in case y is less than equal to x, then y is acting like a lower bound for x and y. So x meet y is y. So if you pick up any two real numbers, they will always have a meet in the set of real numbers. So in this case we can see that the subset S that we have taken is the set consisting of two elements x and y, and these two elements x and y are both real numbers. So this subset that we take in this particular case A, this is a subset consisting of two elements only. But if you take S to be any subset of R, it is not necessary that the meet of S is existing, because the meet of S we have just in part A, I have just told you that meet of S will exist if S has two elements x and y, because x meet y will always exist no matter what happens, whether x is less than equal to y or y is less than equal to x, but x meet y will always exist, which means that the meet of S will always exist provided x and y, provided S has two elements x and y. But in general you cannot say that the meet of S will always exist for any subset S of R. For example, if you take the subset S of integers of the set of real numbers, or the subset S of rationals for the set of real numbers, then the set of integers, the set of rationals do not have a meet, they do not have a infimum, because the set of integers, set of rationals do not have a bottom element. There does not exist any real number x belonging to R which can act as a lower bound for the set of integers, or which can act as a lower bound for the set of rationals. So there is no lower bound for these two subsets, or there is no bottom element for the set of integers, for the set of rational numbers. So because there is no lower bound for these two sets, so definitely the question of greatest lower bound doesn't arise. So greatest lower bound of Z doesn't exist, greatest lower bound of Q doesn't exist, which means that the meet of S, which is the infimum of S, which is the greatest lower bound of S, where S is Z or S is Q, this does not exist. So in this case of real numbers, although a set consisting of a set S, let me write over here, a set S consisting of two elements always has a meet, but in general you cannot say that every subset S of R has a meet, as we have seen in this case. So now then the next question which arises is that if we want to talk of the meet of the set of real numbers, does it exist or not? Now meet of the set of real numbers would be infimum of R, or greatest lower bound of R. Again, that doesn't exist for the same reason, for the same argument, because there does not exist any real number x in R such that x is less than equal to R for all R belonging to R. There is no real number which is less than all the real numbers. So the set of real numbers doesn't have a bottom element. It doesn't have a element which is smaller than all the real numbers, which means that the set of real numbers doesn't have any lower bound. Or we can say that RL, the set of all lower bounds of the set of real numbers, is phi, and because there is no lower bound of the set of real numbers, so obviously the greatest lower bound cannot exist, which means the greatest lower bound of R cannot exist, which means that the meet of R, where R is the set of real numbers, this cannot exist. So that was all about lower bound and greatest lower bound and meet, these concepts in a partially ordered set.